Welcome back. Session 7, Part 3, Bayesian classifier, Bayesian technique, Bayesian theory. We are going to discuss another aspect of Bayesian theory. We try to demystify that, giving a pictorial approach as well as a tree-like approach to make sure everybody is comfortable with that idea. It's really not supposed to be difficult to comprehend. And I hope it is now simple to understand. But before I go to my full example, I would like to explain another viewpoint on Bayesian theory that is going to even simplify further, and that's called naive Bayesian technique. Naive. Naive means weak joints, weak connections, right? That's what naive says. So in the equation we have talked about, C is standing for classifier. Again, this is a general formula, and it doesn't matter how people actually write it and how people they explain it. So it says if C event, if X has already happened, what's the probability of C happening? And the way we are going to calculate that is very easy. This is going to be the common part between C and X. So X common C, that's what the top, the numerator is. And the bottom is going to be the probability of X itself. We said that this is a posterior event. We are going to talk about it in a moment in the example we have. But if you take a look at this whole exercise, so the numerator is going to be CK. Suppose that you have multiple features. Suppose you have many features, not just one feature, as in X. So what happens is that you need to combine the classifier, the C event, and then the X up to Xn event, right? So this comma, as we said, is actually the common part we spoke. So it's going to be CK common part X1, common part X2, common part all the way Xn. That's going to be the numerator. Now, if I wanted to calculate that, what do I do? If you take a look at this on top, you can actually start expanding. So instead of CK being first, I can potentially, because it's common part, right? You could potentially switch them over, and there is no harm in that, as we have shown. So P of A and B is equal to P of B and A. So they are the same. So what we are going to do, we are going to actually put the CK on the other side, and then let's begin breaking down this in the bigger picture of things. Remember, when you have multiple events, how do you handle that? Go back to the Venn diagram when you had A, B, and C at the same time. That was the tree. You could potentially have 10. Right now, we have X1 to Xn, okay? So that's what we have. Now, so I'm going to extract X1. So X1 is going to come out. It's going to be X2 and CK as my existing event, and then X2 up to CK becomes the actual event that I need to put in. Once again, I'm going to extract X2, X3 is left up to CK. If I extract X3, X4 up to CK is going to be left, and that's how I'm going to actually expand this until I get to Xn. So Xn minus 1, Xn and CK, Xn and CK, and then I'm going to have the PCK. So that's that was what this one is. Remember, we switched them over. So this is an exact match, no question asked, okay? In the naive Bayesian technique, we are going to have conditional independence between variables, x1, x2, up to xn. In majority of the cases, perhaps, we would say that these events are not necessarily related in any way. One of them being in a state alpha or a state beta has nothing to do with the other one in a state gamma and a state theta. Make sense? So if we assume that they are mutually independent, what we could do is this. Really, when we say XA versus xi versus xi minus 1 up to ck, really these variables are not supposed to play a significant role anyway. And if that's the case, then I would potentially replace that, potentially, if it is mutually independent, fully independent, then you can potentially say XA, who are these? They are not actually going to be contributing factor to XI. So I'm going to say XI, Y, CK is happening. Make sense? So these two will be the same. So what could I do? I could say X1 line CK, X2 line CK, XN minus 1 line CK, XN line CK, and then PCK, right? Make sense? So if that's the reason I could do that, because I'm assuming they are independent. Really, the presence of X1 has nothing to do with the presence of X2, X3, X4 up to Xn. That's the assumption. So if that happens, I could potentially replace the whole game with the multiplication of X1 line CK, X2 line CK, Xn minus 1 line CK, Xn line CK, and then PCK. So that's what this one is going to be for my statement here. Okay. So that's going to be my case. And then obviously we are going to make it this way simpler. And then we are going to say, listen, you just had the numerator calculated, and then the PX is going to be a constant. And if PS is going to be constant, I'm going to represent that by 1 over Z. So 1 over PX, I'm going to call it 1 over Z. If I say 1 over Z here, then these two would be quite proportional, quite related, possibly even equal, I would say. So what happens is that it would be a lot simpler to basically calculate it this way by doing the independence test with the independence assumption. With that in mind, I want to explain a full example. This is a famous example almost everybody is using on the internet. I have outlook. This is an attribute. Temperature, humidity, windy, and play, the outcome, the target, the result, the final point. To play yes or no. Tennis maybe, football maybe, whatever it may be, to play outside. So outlook has a number of values: sunny, overcast, and rainy. Temperature is going to be hot and mild and cold. Humidity is going to be high and normal. And windy is going to be weak, strong, and that's it. And then the target column, this column, is going to be yes and no. That's what we want to do. We want to classify on the yes and no. It's kind of a binary at this time, okay? Now, if I just look at the whole solution space that I have, and then map the target column to my whole solution space, what do I get? So let's say play. How many times do you have yeses? Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's going to be 9. And obviously you have 14 rows. Keep in mind the first one is the label row, so that doesn't count. 15 minus 1, 14. So 14 minus 9 is going to be 5. So what's the probability according to my table? And keep in mind, this is a sample you already have. And the sample is not infinite. It's not going to be the entire population we are talking about. The reason being is that you didn't even have all of the combinations in place to see what happens yet, right? And the combination would be 3 times, 2 times, 2 times, and 2. So that would be 8 times 3, 24. You didn't have 24 events to cover all of the potential combinations. So that's the assumption. The assumption is you're human and sampling is within your limit, okay? So 9 over 14, 5 over 14. So that's going to be my probability. That's the probability coming from the sample. Keep in mind that if you add this, this probability, you must get 1. It's a very easy test, okay? So 9 yeses over total 14, that's 0.64. 5 no's over 14 total, that's 0.36. That's how we calculated it. Now, here is the question. After saying this, after doing all of this, you get a case in front of you. The case is simple. outlook is sunny, temperature is cold, humidity is high, wind is strong. Do you play or not? Now, let's make some sense into this. We are human beings, and let's understand what this means. So you have sunny here, you have cold here, of course, you have high here, and you have a strong. But let's take a look. Do you have all of them at the same time? Sunny, hot, that doesn't work. Sunny, hot, doesn't work. Sunny, cold, yes, it does, but it is normal. It's not high, doesn't work. Sunny, and that's it. This combination does not exist. This combination has not happened. The question is, if this combination is presented to you, will you play or not? So that's what we are trying to answer. Will you play or not? Will you classify this as yes or no? Okay. Now, with that in mind, I want to play this with a kind of a intuitively and see what happens. Again, remember, we are human. The sample is extremely small. When the sample is going to be really large, you can't do what I'm about to do. It's not going to be easy to do it that way that I'm trying to do. Sunny. Okay, so this is sunny. And then you say high, and then sunny, high, you say no, no. And then sunny, high, you say no. And then sunny, normal, you say yes, and that's it, right? And sunny, normal, you say yes. So if I take a look at that, it seems that the fact that the humidity is high is actually pushing me toward no. It seems that the weight of the decision, according to existing sample, is going to be no. Why? Because sunny and high is no, sunny and high is no, and then sunny and high is no. You've got three no's, and then you don't even have normal. You could say normal and then yeses, and then you can say normal and yeses. It seems that the fact that it is high in humidity is pushing you toward no. Let's take a look at a strong. Sunny and a strong no. That's kind of supporting argument for no. Sunny, sunny and sunny and strong. Sunny and strong, yes, that's 50-50, and that's it. So the fact that this is strong, that doesn't actually help much. It's kind of 50-50, right? But the issue is that you're actually putting all of that in. Take a look at cold. I hope you have a cold. So sunny, cold, you have a yes, and there is nothing else. So the question is going to be kind of difficult to make at this time. But you can say, okay, the humidity high is potentially going to say no. We want to actually understand the classification result using a Bayesian technique, Bayesian classifier. How many sunny days? And the way my human brain actually acted is simple. How many sunny days do I have? I have 5 out of 14. So 1, 2, 3, 4, and 5. How many cold days do I have? I have 3 here, 4, and that's it. How many high humidity I have? 4 and 5 and 6 and 7. And how many strong days I have? I have 1 and 2 and 3 and 4 and 5 and 6. So that's, I'm going to count them, easy. So you're going to count the outcome. Then you're going to count the value-based probabilities, and you're going to have them actually here listed, okay? Now, the event I'm looking for, this is called event. This whole thing is one event. This is called X. So this event X, what's the probability of X happening? Well, outlook sunny is 514, temperature cold is 414, humidity high is 714, and wind strong is 614. And I said equal to 0.022. I made a little assumption here, and I made the assumption that the fact that the outlook is sunny and the temperature is cold and the humidity is high and the wind is strong have nothing to do with each other. I made this assumption to simplify, to make it easy for myself. And therefore, I assumed a kind of a weak dependency, or I might dare to say the full independency. Zero dependency, if I would say, okay, or full independency, the other way around. Calculating the rest is going to be actually easy. Now, I'm going to target the sunny versus, I'm going to actually take a look at the value versus the target in all of these cases. So take a look at this one. I have yes and no, and I have sunny, overcast, rainy. Temperature, yes and no, hot, mild, cold. Humidity, yes and no, high, normal, and then wind, yes and no, weak and strong. So take a look at this. I have sunny, I'm going to count them. If you take a look at the table, and it is available to you, by the way. If you take a look at the table, the sunny with the sunny is going to have 2 yeses. So I have 1, 2, no, and then no, 3, and then 2 yeses. 2 yeses and 3 no's. I can count the overcast. I have a yes, I have a yes, I have a yes, and I have a yes. So I have 4 yeses and 0 no's. Then I have rainy. If I take a look at the rainy, I have yes and yes, that's 2. Rainy, that's 3. And then 2 no's. So 3 yeses and 2 no's. So I could potentially do that. Now, I want to calculate the probability against the target. So probability of yes is going to be, keep in mind, all of the yeses is 9 and all of the no's is 5. 5 plus 9 is 14. So this is going to be 2 over 9. Because this is 2 over 9, this is 4 over 9, this is 3 over 9, which becomes 1 over 3. That's what the Excel does automatically for me. Now, if you take a look at the no column, it's going to be 3 over 5, 0 over 5, and 2 over 5. Now, if you add 2 and 4 and 1, you're going to get 5. You're going to get 7. If you add 3, 0, and 2, you're going to get 5. So that's what you need to keep in mind, okay? This one. Now, 2 and 4 and 3. So that's going to be 7 and 2, 9. 3 and 0 and 2, that would be 5. So this is supposed to be 9. Remember, this is automatically changed by Excel file. The denominator is not the same. And then this is going to be 5. So this is going to be 9, the yeses, and 5 the no's that I have. So if I need to be careful about the entire plane. Okay. So I'm not talking about overcast in my X. I'm not talking about rainy in my X. I'm just talking about sunny. So what's the probability of being sunny if I played? If I went outside and I played, I actually played. What was the probability that the weather was sunny? So yes, and the sunny, that's going to be 2 over 9. I actually didn't play. What's the probability that it was sunny? Very clear, 3 over 5. Make sense? So I'm actually asking you to calculate these because in a moment they are going to actually switch their placement and the question is going to be different. What is the question here? If you saw me playing, what was the probability that the outlook was sunny? If you didn't, if you verified that I did not play, what was the probability that it was sunny? And you can repeat this for the rest. So if you repeat this, if you saw me playing, what's the probability that it was cold? If you saw me playing, what's the probability it was high? And what's the probability it was strong? Each one of them individually, by the way. I'm talking about individual events. I'm not talking about combined events. And I put the color black to represent the yes play, and I put the color red to represent the no play, okay? So in the naive calculation, what do we do? What's the probability that I played and the X event happened? Now I'm talking about event X. I'm talking about all 4 of them happening at the same time. This is my event X. Sunny, cold, high, and strong. So let's take a look. What's the probability that if I played, what's the probability that X happened? And of course, times play yes. So that's what I'm going to calculate. Remember the 2 sides of the equal equation in the Bayesian theorem. I encourage you to go back to the preceding recording to basically get to the idea of the Bayesian theorem, the two sides of the, I'm trying to calculate one side, and then I'm going to resolve the unknown on the other side. So in this case, play yes, and X happening, what happens? So with the independence in mind, this is going to be 2, 9, 1/3, 1/3, and 1/3. That's what we are going to have. Okay, take a look at my my black lines. 2, 9, 1/3, 1/3, 1/3. I assume that they are independent. The fact that it is, for example, cold doesn't mean that the humidity is high. They are independent, right? With that in mind, and then they play yes is 0.64. And then I got the yeses. One side of the equation, I found it. You could potentially do the other side. You could say play no, and then what's the probability that it is play no and the event X happening? What's the event X? The event X is actually all of this. The event X is going to be all of this, and you remember we calculated them already, and they are red, and we basically calculated them according to that table. So 3/5, 1/5, 4/5, and 3/5. So this is what we are going to get, and we multiplied them because we assume that they are independent. They are not reliant on each other. There is no relationship between them. And then the play no is going to be 0.36. What did I do? I calculated one side of the Bayesian equation. What is the px? Do you remember that I needed to have px in the denominator? So I need to calculate the px. Okay, so that's what we had in mind. So I need to calculate the x itself. Remember, px was under the in the denominator, under the fraction. I need to calculate that. So outlook sunny, temperature cold, humidity high, wind is strong. I'm going to multiply them again, and I'm going to get 0.02186. Remember, I have made the assumption that they are independent, and they are coming from rows 16 and 17. We have already calculated them here and here. Remember that? And if you want to refresh your memory, please rewind this recording and then go back and see what we have done, we discussed at that time. So what are we trying to do? Remember, the Bayesian theorem has a multiplication on the left and a multiplication on the right. What do we have? Play is equal to yes while x happened times px is equal to x happened when play is equal to yes times play is equal to yes. So that's what the Bayesian theorem is. I'm going to call this a C. And this C, as you can see, is here. This is my C. This is my C. So this is x play is equal to yes, x play is equal to yes, play is equal to yes, and I calculated the y already here, the yeses, okay? That's my target point. And then I need to find the play yes while x happened. What am I trying to do? Here I said, if you saw me playing, what's the probability event happened? Here I'm saying, if the event happens, what's the probability I'm going to play? That's where the priori and posterior are coming into play. And this is what we are trying to do. This is called posterior. Event has happened. What's the probability is going to be yes, that I'm going to play? So it's equal to the constant divided by px. We also call this a normalization. We call this a kind of a normalization that we want to do. So what's the probability event happens, the x, the whole of x happens, and then I play. And it's going to be the C divided by this constant px, okay? Be px. And I'm going to say 0.2424. And the reason we call this normalization, because obviously, as you can see, things are not balanced in my table. My table is small. Sometimes I might have actually skewed toward one of the others, one of the values versus the other, one of the classifiers, classification versus the other. Because I'm skewing towards some, I'm actually trying to divide it so that I am going to make it normalized. That's why they call it normalized. Now, let's repeat the same thing. If you haven't captured what we have discussed here, let's repeat this, and hopefully in this one, with this repetition, you're going to capture it. Take a look at the Bayesian theorem. It says, what's the probability that X has happened and I didn't play? Times X happens, the probability, is equal to, what's the probability that play is no and X is happening? I didn't play and X was there. Times play as equal to no. I'm going to call it K because this is not the same constant as this one. So I'm going to call it K. Now, with that in mind, what am I looking for? What's the mystery? The mystery is simple. What's the probability that X is happening and I'm not playing? This is posterior. X is happening and I'm not playing. This one says, this one says, play, I'm not playing and X has happened. This is superior. This is posterior. X has happened. What's the probability I'm not playing? Is equal to K divided by PX. So what do I get? It's going to be, what's the probability of X happening and I'm not playing is equal to K. This constant, this K, has already been calculated here, 0.0206. Okay, divided by PX. PX, as we said, is constant, and it is a kind of a normalizing factor. So I'm going to put that in. That's why we call PX in the early session of this recording to be a constant, like 1 over Z. We didn't ignore it though. We have it, it's still here. Now, if you take a look at this, I'm going to ask you this simple puzzle. With all of the calculation in mind, I want to ask you this. What's the probability X happens and you play? What's the probability X happens and you don't play? What's the probability of X happens and you play is 0.24. What's the probability of X happening and you don't play is 0.94. 0.94 is bigger than 0.24 and therefore you don't play. This is a classification problem, and you're classifying and you're saying, if you wanted to classify the X event, what would you classify it? Would you classify it yes, or would you classify it no? And you're going to say, I'm going to classify it as no. And if you had gone to that table, you might have potentially said, I think the weight is toward no. But that's intuition. And this is a very systematic approach to actually say whether there is a yes or no. So this is a very simple example. I would like you to pick up the empty Excel sheet and then try to redo everything, as I said, in the Excel file. And then hopefully you're going to come to the grip of what this means. Remember, this is the entire game. This equation, the Bayesian theorem, is the entire game. This is the entire game. And then eventually you're going to compare this versus this and then make a decision. And that's how you're going to do. Now, there is a small side note that I want to do. We assume that these events, the events that we spoke of, is outlook, temperature, humidity, and windy, are independent. Okay, there is a simple test, and the simple test is this. First of all, if there is a plain no, and what's the probability of you had yes and the X happened? Of course it's 0, because these two are not related, right? So you can imagine that these two are not, you can't say play no and then you can say play yes at the same time. You can't do that. You can't say play yes and they say play no at the same time. I should not have used the multiplication. I should have used some notation, a relationship, right? What's the relationship between these two and this? I shouldn't say multiply. So I'm going to say, what's the relationship? If you haven't played, how come you played? And therefore, this is going to be 0. Now, when you take a look at the summations we have, the summation we had, for example, for the no's is 0.0206, for the yeses 0.0053, you add them up, it's 0.0259, okay? So, and that's not what we get in our calculation. But the difference is very minor. The difference is very small, and it shouldn't be interfering with our process. So naive Bayesian technique is meant to simplify the things for us. Oh, I wanted to compare this 0.0259 versus 0.02186, for example. They are close, but they are not the same. Now, with that in mind, this is a simple example. We made an assumption that the attributes are independent. They are not interfering with each other. I would like you to make that assumption for now. Unless you are, as a domain expert, you are going to move away from a naive Bayesian technique and go back to the full Bayesian technique, and you need to actually calculate the relationship, conditional probabilities and all that, and then do the job right. But at this time, let's assume and simplify and make it a naive Bayesian approach. And the question is, if I have an event, whether do I play or do I not? And for that to happen, while you could do intuitively, we have a systematic approach to actually do that. Don't forget the normalization. Don't forget the fact that you're going to divide by a constant px, and that's how it's going to be, okay? With that in mind, the example is over, and part 3 is also done. Thank you very much. Stay tuned for part 4. Thank you.